Hello everyone.
Hello everyone. Hello everyone.
So, welcome to the second day of the National Workshop on MATLAB for Physicists. So this is the first session in the second day. So in the previous sessions, we have seen about basics of MATLAB, how to deal with matrices, and a few graph plotting techniques. So today, in this session, we'll see a few applications of this MATLAB in various fields of physics. Okay, so shall we start? Okay. Okay. So the previous session was in about Lisa's figures, drawing graphs. So we'll continue that. We'll continue with another topic is on Fourier series. How to draw the Fourier series. Let's say I consider Fourier series for sine wave. Sorry, Fourier series of square wave. Let's say if I consider Fourier series of square wave. So a square wave is obtained by mixing sine waves with different frequencies. Okay. So somehow we have to write this function sum over 1 by n sine n pi x by l. The function is f of x is equal to 4 by pi sum over 1 by n sine n pi x by l. This is the Fourier series for square wave. So a square wave is obtained by mixing sine waves with different frequencies. So n is the variable. Sum over n. And we have to add only the odd terms. 135 sum over 135 up to infinity. So we'll see how better square wave generated by increasing the number of waves. Okay. So I'm going to editor and I'll write a new script. I save it as a square wave. So if you need a space, you have to use underscore in the name of the file. Square underscore wave dot m. Square underscore m dot m. Underscore wave dot m. So my sine function in the theta value varies from 0 to 2 pi. So I'm defining that. X is equal to 0 to 0.1 to 2 pi. Just a minute. X is 0 with a step size of 0.1 up to 2 pi. Then I have to add, let's say I'm defining n is equal to 5 for I is equal to 1 to n, and we have to consider only odd terms. So my step size should be 2. For I is equal to 1 is to 2 is to n. That means I starts with 1 with a step size of 2 goes up to n. I is equal to 1 is to 2 is to n. For I is equal to 1 is to 2 is to n. So my total term, the thing I need to plot, I call it as f, and I'm initializing it to 0. F is equal to 0. So for I is equal to 1 is to 2 is to n, I'm updating the value of f. F is equal to f plus sine otherwise I call this as capital N and my loop index small n. So capital N is equal to 5 and loop index small n is 1 to 1 is to 2 is to capital N. Then sine n star x by n. Plot x comma f. So this is how I get a square wave. Near to square wave. So if I increase the number of waves, let's say if I take 10, I get a better square wave. To see the contributions from all other waves, I need to plot other waves also. So I'll include here the contributions from other waves. So before that, hold all, and plot x comma whatever that individual contributions that we are considering, sine n star x. So I'm holding all, and I'm plotting individual waves that I'm considering into this summation. So I'll start with lesser contributions. So I'll start with 5. So this is the ultimate configuration. Let's say if I want to increase the line width, comma 2. So it has contributions from 3 sine waves. 1 with unit frequency. When within 0 to 2 pi, we have a single sine wave. Second wave with double the frequency. So that could be the blue one. So by joining 3 sine waves, we have got a square wave like this. So if we increase the contribution of waves, the square wave becomes better and better. So if I increase n value capital N to 15, I'll get a better square wave. So this is how we can plot Fourier series for square wave. And we can verify how better the square wave improves with contribution from additional terms. Let's say if we want to generate a sawtooth wave, the Fourier series of sawtooth wave. The equation in Wolfram math world is more convenient for us to write a program. Right. So the sawtooth wave consists of this 1 by 2 minus 1 by pi sum over 1 to infinity 1 by n sin n pi x by L. So f of x is 1 by 2 minus 1 by pi sum over n is equal to 1 to infinity 1 by n sin n pi x by L. 1 by n sin n by x by L. So I consider only functional form dependency. So here 1 by 2 minus sum over 1 by n sin n by x by L. Sum includes all terms, both even and odd terms. N takes values from 1 to infinity. Okay, so I'm copying this entire program, creating a new file. And saving it as sawtooth.m. Sawtooth.m. So here we have to consider sawtooth.m. So we have to consider all the terms, both even and odd. So I'm taking n is equal to small n is equal to 1 to capital N. So f is equal to f plus sin nx by n. So here my initial value of f, I'm considering it to be 1 by 2, and all incoming terms are being subtracted from it. So my initial value of f is 1 by 2, and in the loop I am subtracting every term. F is equal to f minus sin nx by n. So I'm starting with 3 waves for better visibility. Oh, sawtooth is a built-in function, so you cannot use that. Sawtooth is a built-in function. So place underscore in the file name. Save file as, that is also not possible, saw underscore tooth and delete the earlier file. Saw underscore tooth.m and delete the earlier file. You have to delete this file, sawtooth.m. So my file name is saw underscore tooth.m. So I got a sawtooth wave like this. So here the amplitude is 2 units. Maybe that 1/2 should be included everywhere in every term, probably. This has become off. So anyway, this is the graph. And if I increase the number of terms, I'll get a better sawtooth wave. So if I increase more and more number of terms, the curve smoothens. So what is the additional quotient that we are missing here? One by pi. So include that also in the summation 1 by pi. So whatever. So this is why we plot a sawtooth wave. So other functions also can be plotted in a similar fashion. So that's about Fourier series. So after this, we'll go. So we'll go to Kepler laws. So we'll try to plot the shapes of orbits. So we'll try to plot the shapes of the orbits. Kepler problem. So coming to conic sections, like when you try to draw a ellipse, parabola, or hyperbola, it will have two focus points. You have two focus points, and radius is not a constant. I mean, for circle, radius is a constant, but for all the shapes, radius is a function of eccentricity. Okay, so I'm considering A is equal to 1, length of semi-major axis, and eccentricity 0.2. Now the radius varies as A into a new file. So open a new file and save it as Kepler.m. Kepler.m, and here the angular part is varies from minus 2 pi to plus 2 pi. For ellipse, it is only 0 to 2 pi, but for parabola and hyperbola, there is a negative side of the curve also. So we have to take the theta part from minus 2 pi to plus 2 pi. So t value varies from minus 2 pi to plus 2 pi with a step size of 0.1. And I'm taking A is equal to 1. Length of semi-major axis 1. Eccentricity, let's say if eccentricity is 0, we should get a circle. So I'm starting with E is equal to 0. And R is equal to A star 1 minus E square by 1 plus E cos t, E cos theta. So here we have to use a dot. And also take care of brackets correctly. So A star 1 minus E square dot slash bracket 1 plus E star cos t. Just similar to our Lissajous figures, we have to resolve x component and y component. X is r cos theta and y is r sin theta. Then we have to plot x and y. So for convenience, I'm plotting the focus points also. The focus points will exist at C0 and minus C0. X and Y calculations also I'm using R dot star cos t. Y is R dot star sin t. So if I run that, I get a circle. I mean, if you stretch it, you'll see any shape that you want. But to confirm the shape of it, you have to see the scale. So it extends from -1 to +1 along x-axis and -1 to +1 along y-axis. So it is a circle. +1. So we get a circle. So if I change the eccentricity, I should get an ellipse. So along x-axis, it is extending from -1.5 to +1.5. So it is 3 units. So this is my ellipse. And when eccentricity is equal to 1, I should get a parabola. That's it. This is a hyperbola. I can just zoom it and see. So to zoom the plot, I'm selecting the zoom tool. So it is better to fix y limits. What if I fix x limits also? This is a situation when I fix my x limits. E dot square. Here E square. Minus 2 star. So if you change the limits to so this is how you got a hyperbola. So to see all these plots in a single graph, I'll use a for loop or E. So I'll use a for loop. So for E is equal to 0, 0.3, 1.2. And I have to hold all. Hold all. For E is equal to 0 to 0.3 to 1.2. Now if I run this, the first one is a circle that runs from -1 to +1. The blue one is a circle, so I have to adjust it to the shape of a circle. Then we can see all other the red, orange curves are elliptical in shape. So this is how we can plot various shapes of orbits with variation in eccentricity. can access to your phone. MATLAB ఉన్నారా? Use your phone. Mute లో పెట్టేసి. Okay, so this is about Kepler orbits. So next one, I'd like to plot a spiral. So here we come across a 3D plot. So I try to plot a spiral. So this program is generated by ChatGPT. Simple program. Line 13. Go for next one. Next one. So I'm considering n number of turns. N turns is 10. So I try to plot 10 loops in the spiral. And Z max. So the height of the spiral is 20 units. So within 20 units, I try to plot 10 loops. And radius is 5 units. And I want to have 1000 points. So n underscore turns. N underscore turns is 10. Z underscore max is 20. Radius is 5. So open a new file and save it as spiral.m. Yeah, spiral.m. So the text after percentage symbol is considered as comment. That will not be executed. So you can write whatever you want for your understanding after a percentage symbol. Desktop mode and continue with the desktop mode. Continue web browser options. So for theta, so theta value is now running from 0 to 2 pi n turns 10 times. So it is running from 0 to 2 pi 10 times. So 0 to number of turns multiplied by 2 pi with a step size of number of points 1000. So from 0 to n number of 2 pi's, we have 1000 divisions. So for that purpose, I mean, to fix the number of divisions, we use linear space. So I'm considering n turns, 10 turns along z axis with the 20 units with radius of 5 and 1000 points. And after that, I'm generating x and y as usual. R cos theta, y is r sin theta. Z value 0 to z max, 1000 divisions. So if I run the program, I get a spiral axis. This is actually the space-time plot of a orbit. So even if a planet revolves in a circular orbit, if you include time along z-axis, so circular orbit comes in xy plane. So if you include time along z-axis, by the completion of one circle, time axis increases by 1 unit. Along time axis, value increases by 1 unit. So a spiral will be generated. So spiral will be generated. So this is what we use in general theory of relativity to plot space-time curves. So here I'm considering only circular orbit with an extension along z-axis. So the circular orbit becomes a spiral. So instead of circular orbit, if you alter the radius just similar to Kepler orbit, you'll get all other shapes like elliptical orbits, parabolic orbit, hyperbolic orbit also can be generated if you alter the function of radius. So that can be done in this fashion. I mean, if you include semi-major axis and eccentricity, you can define your new radius. That modifications can be done easily. So this is how space-time plots can be generated in 3 dimensions. These are the other. ఎక్కడ XY Z lens space 0 Z max then underscore points. Bracket close percentage symbol. Shift. So is that over? Shall we proceed to the next task? Okay. That is all. We'll proceed to the next task. So here we can plot orbitals. So here it is considered n is equal to 3, L is equal to 2, and M is equal to 0. So it is in third orbit. In third orbit, d orbital, and M is equal to 0, probably d z square. That is a d z square orbital. It comes out to be dumbbell in shape. So I mean, don't need to write this program. I'll share it. I'll explain it and I'll share the code. So here theta is considered to be varying from 0 to pi, and phi value is varying from 0 to 2 pi. And a mesh grid is created with theta and phi. So here the theta deals with z direction variations. So that varies from 0 to pi, 0 to 180 degrees. And phi is deals with the variations in xy plane. So it varies from 0 to 2 pi. So on xy plane, we develop a circle, and if we extend the circle from 0 to pi along that direction, it becomes a sphere. So we can generate a 3D structure by varying theta from 0 to pi and phi value from 0 to 2 pi. So and a mesh grid is generated with theta and phi. And now R value, the radial function is being generated, square root of 2 by n cube e power minus r by n, r power L. And we have to generate spherical coordinates. So YLM is initialized to zeros, and PLM is a legendary function. This legendary function is a built-in function. So it takes so for Octave 9, it is a built-in function. For earlier versions, you may need additional toolbox. Okay, so for Octave 9, 8 and 9 onwards, it is a built-in function. You can see the help for that. Help legendary. So all special functions are now built-in functions for Octave. So legendary takes input n and x. So n and L values. And any normalization constant. This is not necessary for the time being. So let's say n and L values. Let's say legendary 2, 1. You get 3 values. Two comma 0. So L value should be always less than n. So if I place 2, it is an error. So legendary function takes n and L values as input, and L value should be less than n. So legendary 3, 0 will get some output. So in third orbit, you will have 4 orbitals. Is it? 0, 1, 2, 3 orbitals. Three 0, 3 1, 3 2. Oh. So this should be less than 1. Okay. So theta value. So theta value should be between, cosine theta. Cosine theta value varies from 0 to 1. Minus 1 to 1. Let's say if I place minus 1. Yes. So cosine theta value varies from minus 1 to 1. those values will vary between -1 to +1. That is what this PLM is a legendary function, legendary polynomial. So it takes the inputs for legendary function are legend 1 or whatever L value and cosine theta. So once you go for that, you can generate the YLM values and the wave function. You can construct the wave function by considering radial part multiplied by the angular part. So at the end, we have to resolve XYZ components. So X component is R sine theta cos phi, Y component is R sine theta sin phi, Z component is R cos theta. So with these inputs, we can plot various shapes of orbitals. And there is a well sophisticated MATLAB file already available on MATLAB website. So the file available in MATLAB Central is this. Plot hydrogen molecular orbitals. Share that file. So here N is 3, L is 2 and M is 2. So this is a double dumbbell d orbital. So I'll share that file link. Probably this is the file. You have to register with your email ID and download it. Registration is free. So you have to register with your email ID and can download. I share the file in WhatsApp. So by varying these values, you can generate different orbitals. So n is equal to 3, L is equal to 2 is a third orbit, d orbital, m0, dz, dz square orbital. So it will be extended along z direction, dz square. Let's say if you want to plot px or py. So L should be 1 for p orbital. M is 0 for pz. You get dumbbell. This is the dumbbell shape. And for d orbital, it is double dumbbell. Double dumbbell. So you can vary different values of n, L, and m values. So n should be 4. If you want to plot f orbital, we'll try to see. This is f orbital. N is equal to 4, L is equal to 3, and M is equal to 3. So you get 6 rows. So this is how you can plot different molecular orbitals. atomic orbitals. So at this level, we take a break for 10 to 15 minutes. We'll come back by 11:45. So there, then we'll see differentiation, differential equation solutions, all those things we'll see in that session by 11:45. Please turn on your camera so that you take a screenshot. Okay. Okay, so shall we continue? So now we will go through symbolic calculations. So instead of just numerical calculations, you can go for symbolic calculations. Like you'll get results in terms of functions. Even those integrations, differentiations can be performed just by using symbolic calculation. So for that, you need to consider this. Simple harmonic motion. So you need to load the package pkg load symbolic. The symbolic package should be loaded first. Then you have to define your variables. The variable definition should be in terms of sims. SYMS. SYMS is a type of variable, symbolic variable. So y of x is a function. Y is a variable which is a function of x. So that is what sims y of x stands for. Sims y of x. And I am writing a differential equation for simple harmonic motion. The equation one is second order differential equation d square y by dx square. That is what if y comma 2 stands for. If y comma 2 stands for d square y by dx square. is equal to minus 25y. So it is, I'm considering omega value to be 5. So d square y by dx square plus omega square y is equal to 0. So like that we have to write our equation, and we have to keep the first term on left side and take all other terms to the right side. This is how we have to write differential equation. Write equation 1 is equal to whatever first term, or the higher order term should be on the left side, and there will be double equal to, and all other terms will come on the right side. So this equation is actually d square y by dx square plus 5 square y is equal to 0. And this is a solution. To solve that equation, I have to use the command dsolve. Dsolve is used to solve differential equations. Dsolve, I'm supplying the equation 1 as input, and I'm giving initial conditions. Since it is a second order differential equation, I have to use two initial conditions. y0, differential of y0. So first derivative of y at 0, that value I need to supply, and function value at 0. So for second order differential equation solution, we need two initial conditions. We'll see step by step what happens actually at each level. And then we try to plot it. So if I plot it, actually if I run the program, I'll get a sine wave as a solution. So the symbolic package is getting loaded, so you have to wait for some time. SSM dot. Yeah. Run it. It takes some time. So command will do it. Details installed. Symbolic. Details installed. Block వచ్చింది. And take some time.
Equation 1.
So we'll see what exactly is happening at each level. For that, I remove these semicolons. I remove the semicolon and run the program again. For that, I close the plot. So I got a graph. So if you see, equation 1, d square y by dx square is equal to minus 25y. So that is what we gave as input. And solution for that is sine 5x by pi. So if we don't supply the initial conditions, check what happens. If we don't supply the initial conditions, so plot got an error, that's okay. So the differential equation is d square y by dx square is equal to minus 25y. That part is clear. And we got some constants, c1 sine 5x plus c2 sine 5x. So these c1, c2 values can be fixed only when we supply the initial conditions. The value of function at y is equal to 0, so at x is equal to 0, and the value of first derivative of the function at x equal to 0. We supply these two, then only you'll get a solution, exact solution. So that C1, C2 values are obtained by supplying these initial values. I consider y0 is equal to 0 and the first derivative of y0 is equal to 1. So that means initial velocity is 1 and initial displacement is 0. So the pendulum is starting from its mean position, 0 position with some initial velocity. That is what this initial condition says. And so we got a graph like this. So initial displacement is 0 for this pendulum. Let's say if I start the pendulum at an extreme point, so here the displacement is maximum and at the extreme point velocity is 0. So I'm trying to change the initial conditions. Check how the plot changes. So now the graph starts from 1. Graph starts from 1. So at the extreme point velocity is 0. So let's try to see what happens if the velocity is not 0 even at the extreme point. You will get an error. No, we are not getting an error. So we get a cosine wave. So at initial time, it is starting from 1. When t is equal to 0, it is starting from 1. So f plot is for plotting functions. The solution 1 is a function. Sin 5x by 5 plus cos 5x. So f plot plots that function. Okay, so this is how we write. We try to solve differential equations. So these kind of equations we may come across even in electricity while solving for LCR equations. LCR oscillatory circuits also will have similar type of differential equations. So we go for damped harmonic motion. So I'm using similar equations. So my differential equation now contains damping factor also. A first order derivative. So d square y by dx square is equal to minus 25y minus dy by dx. Save it as DHM data. So here I'm considering omega square is 25 and damping factor gamma as 1. So it is very small compared to the frequency. So if I run the program, get a nice damping harmonic oscillator. right? So I can tweak around the value of damping factor. Damping is very low. It is almost like oscillatory. The damping factor. So let us try to plot everything in a single graph. So I consider it as a variable gamma G, for G is equal to that is how for various values of damping you can see the output. So that is how we can solve differential equations. So you can write any equation. The only thing is the higher order term should be on left side and all other terms should be on the right side. And so this is a solution. 2 root 3 by 15 e power minus 5x by 2. So this is the damping factor multiplied by sine 5 root 3x by 2. So the oscillatory function is multiplied by exponentially decaying function. That is over. We will continue to so now we'll see symbolic integration. So int is a command. This is what sims fx. So it takes some function. Let's say integral x e power x. So I'm taking a new file and I save it as integration.m. Integration.m. So for convenience, I'm writing that pkg load symbolic. Just same as the one that we did for harmonic oscillator. I'll copy this. And I'm defining symbolic function y of x. So here y is what? X e power x. Integration undefined near line 1 column 1. I need to restart. So this line 1 column 1 error occurs when Octave not able to process even the first letter. Integration undefined near line 1 and column 1. So simple solution is just close it and open it. Symbol package is loading. So y of x is equal to x e power x. That is a function I'm considering, and here I'm doing integration. Integral y of x dx. The general solution is x minus 1 e power x. This is the program. Since y of x, equation 1 is equal to y double equal to x e power x. So here you can give limits also. Integral 0 to infinity, let's say. So result is an infinity. Integral 0 to infinity y of x dx, which is x e power x dx. So instead of infinity, if I put 1 as upper limit for integration, I got 1. So it is integral 0 to 1 x e power x dx. The result is 1. You can play around any manner. Not working. Okay. That's all. That's how you can perform symbolic integration. Uh, so if you supply the limits, you'll get exact result, and if you don't supply the limits, you'll get functional form of solution. So if you don't supply the limits, you'll get functional form of solution like this. Integral yx dx is equal to x minus 1 e power x. Okay, the same way you can go for differentiation also. That is available at the bottom of the diff. So you can write it as an equation directly. Instead of defining it as a separate variable, you can write it as an equation. So alternative form for this. Take a new function, a new file, save as integration 2 dot m. Copy paste the existing program. Since y of x, write y of x is equal to x e power x. Integral y check whether that works or not. Integration to yx is Sims function x e power x. So it is working. If you remove the limits, you'll get functional form of solution. Integral y, which is integral x e power x. So if you program, you get functional form of solution, which is x minus 1 e power x. So you can write the equation directly like this. Same way you can try differentiation also, numerical differentiation, sorry, symbolic differentiation. So I'm opening a new file with the name diff1.m. Because diff is a built-in function, you cannot use that. I'm using diff1.m. diff1.m. So PKG load symbolic. Sims y of x. Sorry, f of x. Okay. F of x is equal to sine x square. F of x is equal to sine x square. And this we come across while solving particle in a box related problems. Df is equal to diff f comma x. So if you run this code, symbolic package is loading. The given function is sine x square, and derivative of it is 2x cos x square. So we use substitution method for this. We call x square as y. So sine y derivative is cos y, and we have to differentiate that y. That is 2x multiplied by cos x square. So wherever you need, they can plot the function. F plot. F. So it is case sensitive. So it must be careful while using capital and small letters. So diff is a built-in function, diff. You have to use any other name for your function. So fx sin x square is blue curve and solution 2x cos x square is red one. So you can use these things to solve coupled oscillator equations or differential equations that we come across in circuit analysis, like LCR circuits. Okay. So using MATLAB, you can get functional form of solution also using symbolic package. So that is the advantage. Diff1 data. Okay. So with that, differentiation and integration, differential equation solutions are over. Okay. One more thing. For 3D graph plotting, with this equation, we will close this session for now. So this is the last one for this session. Okay. So here I'm considering, I'm trying to solve charged particle motion in perpendicular electric and magnetic fields. So the velocity of the particle is along x-axis here. I'm considering initial velocity to be 5 units along x direction. And the magnetic field is along z direction. Electric field is along y direction. So I'm considering three vectors. V0 initial velocity, phi 0, 0. Magnetic field B, 0, 0, 5. So it is applying along z direction. Electric field E is 0, 1, 0. It is applying along y direction. So I'm considering 5 units mass and 1 unit charge.
Got it.
And I'm considering the initial position of the particle to be at the horizon, 0, 0, 0. These are my initial conditions. Initial velocity 5 units, magnetic field 5 units along Z, electric field 1 unit along Y, mass 5 units, charge 1 unit, initial position horizon 0, 0, 0.
ఏం చేస్తున్నావు కనబడుతుంది నీకు షూటింగ్ వెళ్ళినావు గన్ షూటింగ్ పోనీలే, ఏదో దానికి హెల్ప్ అయింది కదా.
Dot extension should be dot. So I want to check the time evolution of this system. So initially the charged particle is at the origin, and I want to see its how it evolves as a function of time in terms of its position and velocity. So I'm pushing my initial position and initial velocity as a first row in the series. So row 1, all columns, is now storing R0, the first vector. V, velocity, row 1, all columns, is now storing my initial condition, initial velocity information. And I try to develop other conditions also. I try to develop time evolution of position and velocity. It's the time interval. 0.0001. Equal to 601. G was earlier one. 601. Okay.
Differentiation, regression to
So I'm developing my vectors R and V as a function of time. So I'm taking 10,000 points, I mean 10,000 steps. Starting from, and the step size is this, 0.601 is my time interval. So dr is v multiplied by dt, instantaneous velocity multiplied by time interval. Will give you small variation in the position. So that I have to add to the existing position vector. So n starts from 1, so n plus 1. So the second entry, second row in R is now contains first row elements plus dr. So n starts with 1. So first row elements plus dr gives me my second row element. So that dr is obtained by velocity in first row multiplied by dt. and change in velocity so for that we need to have force by m into dt. So this dv is obtained by calculating a dt. So how do you do that? It is so dv is equal to a star dt and acceleration is f by m, force by mass star dt. This is what we are doing here in the next step. So dv is acceleration times dt and acceleration is force by mass, and the force experienced by charged particle is q times e plus v cross b. So q times e plus cross product of v and b is the force by mass multiplied by dt is dv.
మనకి అవసరం లేదు.
So my final velocity is instantaneous velocity plus that additional change in velocity. So the second row is obtained by dv to the first row values. And then I'm just plotting it. 3D plot of R1, R2 and R3. With line width 2. So all rows first column, all rows second column, all rows third column of R. This is how you get the trajectory of the charge particle. This spiral. If you increase the number of points, you can get a complete spiral. So this is the trajectory of charged particle in perpendicular electric and magnetic fields. So I'm setting the viewpoint at 60 degrees and 45 degrees. That can be altered depending on the requirement. You can just play around. Yeah. So with that, we have covered differentiation, differential equation solutions, and we have seen Kepler orbits, space-time diagrams, charged particle motion in electric and magnetic fields, different types of orbitals, and Fourier series. Okay, so with that, I'm closing the session 1 of day 2. If you have any discussions or doubts or feedback, you can give.
Sir, small doubt. Am I audible, sir? Hello? Hello? Sir, is there any package required to do differentiation and integration, sir? I'm not getting that. Plots or solutions?
Right. So if everything is fine, I'll close the session.
Hello, sir. Can you able to listen to me?
Is that okay?
Hello? Hello?
So R1 comma semicolon implies it is first row and all columns. And in Octave 9, symbolic package is already included. Please install the latest version if you're not able to. Okay. So if the package exists, you'll get an output like this. PKG load symbolic. Okay. So with that, I'm closing the session. And in the afternoon, we'll try to work out coin tossing experiment. Which is essential for entire statistical mechanics. Okay. That's all for now. So we'll meet at short 2 in the afternoon.